right, so now we're going to get into some of the really cool stuff about calculus, a little bit away from the theoretical limit idea-based calculus, and start looking at some of the applications. I've sketched out a curve here. Doesn't have any particular function that I know, but let's just say that the function of x sketches out this curve. And if I were to grab a line or sketch a line or cut a line or slice through this curve using a line, I wonder how many ways I could say that, I would be able to calculate the slope of that line, right? Just by using information that I already know from Algebra 2. So if I have a point here and a point here, these 2 points are where my line intersect on my function, I can write the slope of the equation by writing the slope is, well, I know it's y2 minus y1 over x2 minus x1. But notice I'm keeping everything very general. I don't even have a function, so even if I had an x value, suppose this was 2, I wouldn't have anything I could plug it into. I might have a graph or a table that would show it to me, a plane that would show it to me, but we're just going to try to keep everything really general. So instead of using x's and y's, I'm going to say that the f of b minus the f of a equals b the slope equals the f of b minus the f of a over b minus a. So let's look at that. If I call this point A and I call the x ordinate for this second point B, then the run is equal to b minus a. Okay, so that would be the run part of my slope. So how would I do the same thing to talk about the rise part of my slope? Well, clearly this is my f of a, and this would be my f of b. And so I can say that my rise is equal to f of b minus f of a. Okay, so all I've done is what we have done already for 1,000 years, just change the notation. Rather than using x's and y's, I'm using outputs and inputs. But I want to go a little farther and actually solidify some notation that you've worked with before. I want to take the f of b minus the f of a, which is really just this distance, and call this delta. Remember, delta is the way we say change in. So I'm going to call that the delta y, the change in y. And the same thing here. I'm going to call this delta x. So I could say that the slope of a line secant to a curve is delta y, or the change in y, over the change in x. These two forms are going to come together for us here in a few minutes. So this would be a secant line. Because it intersects a curve at exactly 2 points. That would be the secant line. And this is all well and good, what we've done here, except really all I've done is set us up to do exactly the same thing we've always done at the Algebra 2 level. I've just changed up the notation, so why bother? If it's just a change of notation, why not keep the original notation? Well, we want to take it a little step farther and actually change up the notation. So instead of dealing with b's and a's, two values of x, we want to find out if there's a way to write this whole function or this whole formula with respect to only one x value, and to be able to describe the secant line. And it turns out we can, and I think to show that, I'm going to go ahead and copy the original graph I had here underneath down here. Okay, there we go. So this time what I want to do is identify this lower point as c f of c. So if I label that, that would be c f of c. And then I want to come up with a point coordinate that uses c and f of c in the function, rather than introducing the arbitrary x will keep, but we don't want to introduce another specific value like a or b. So let's look. Well, to go from the first point to the second point, this part has not changed. I could call this second point c plus the change in x, right? Where the distance I travel from c to this second point is just the change in x. So I have an x value, c plus whatever the change in x is. That way, this change can be played with. I can move it around and I'd still be able to use the same formula. Just all I have to change is whatever the distance from c is I'm trying to move. Which means that this point, that the output could be, well, let's not do the ordinate yet. The output then would be f of c plus delta x. So I'd be able to write the function of this point, which is c plus delta x, right? So this ordinate then, or this coordinate, would have this funny long point values as c plus delta x as my x, my input value, and the f of c plus delta x as my output value. So now if I write the slope equation, the change in y over the change in x, I get y2 is the f of c plus delta x minus the f of c over c plus delta x minus c, right? So this is the one point minus the other point. Well, that's really handy because the f of c plus delta x minus f of c over the change in x just reduces to the change in x because c minus c equals 0. Which is a very handy way to describe this because we're talking about our delta y, or our change in y, being a difference between whatever the change in x is and some original c that we plug in. I don't have to know what the second point is, I just have to know how far the change in x was. And the same thing for my delta x, all I have to know is how far did I go from whatever my original point is. In fact, I don't even have to know the original point for the run part of the formula because the c cancels out. Okay, so you're probably still thinking, well, how is that better? Well, here's why we need that. As long as we're calculating the slope of a secant line, we're fine. We have no problem at all calculating the slope, and there's no reason to change up our notation. But we actually want to calculate the slopes of tangent lines. So a secant line touches a curve at two places, but a tangent line touches a curve at exactly one spot. And you saw these in geometry, if you recall. These are situations where you looked at a circle and a tan line had to intersect that circle at exactly 90 degrees, and then you had a radius and you did some calculations with that. So tangent lines are really important in calculus, and so let's go ahead and just use, since we only need 1 point, not 2 points, right, because we turned this into c, let's find the slope of this line. So the slope, which is the change in y over the change in x, equals, let's use this, the f of whatever c is plus the change in x, no problem yet, minus the f of c, no problem yet, over delta x. We have a problem because if you start at c and go nowhere, because this point intersects, or this line intersects at exactly 1 point. In this case, our delta x, which would be c plus the change in x, our delta x actually equals 0 because we didn't go anywhere. Well, I can't have 0 in the denominator. That's a problem for us to solve. Luckily, we have a really great tool at hand, and that is we can calculate the limit, because we don't actually have to be defined at that point as long as the limit is defined at that point. Okay, so the limit as the change in x approaches 0, right? So as these delta x's get smaller and smaller and smaller as your slope starts to approach 0, I'm sorry, not your slope, but as your difference between the 2 points starts to get closer and closer to 0, we can take the f of c plus the delta x minus the f of c over the change in x. Well, we're trying to make the change in x equal 0, but since we're not actually looking at delta x being 0, we're just looking at what's happening as you get infinitely closer to 0, we can actually say what the slope of that tangent line is by using the limit. Also, the slope of that tangent line is something that we call the derivative of x, and it's called, and we write the f prime. So this is this whole thing. Well, actually, I should say this part is the derivative. Well, no, I think it's the whole thing. So this part is the derivative of the derivative of the function. This is the derivative, and it is the derivative equals, holy cow, the derivative equals the slope of the line tangent to the graph. At x equals c. So our x value is something we can plug in now, right? So we have our input value being c. We have something we can plug into our formula or our function, and then we can calculate out the rest of the formula without having to have a second point to find out a slope. Because until now we've always needed a second point to calculate the slope. Now we can calculate the slope with only one point to do it with. That's pretty cool, I think. So we call the derivative the slope of the tan line. In short, we don't say all that. We just say the slope of the tan line. So after that tongue-twisting jumble, let's do an example. Let's get down to the fun of it. So we want to find the derivative, or the slope of the line tangent to the graph, or the slope of the tan line. See, so much easier to say derivative. We want to find the derivative of the f of x equals x cubed plus 2x. So what we're looking for is the slope. So we want the derivative. Well, the f prime of x equals the limit as delta x approaches 0. So the limit as the change in x approaches 0 of the f of x plus delta x minus the f of x, right? So this would just be our c value at this point from the formula we worked with before as we derived this formula, over delta x. Okay, so this is called the definition of a derivative. This whole thing is just the definition of a derivative, or of the derivative. Okay, so let's calculate it. Well,